16.5. The linear wave equation. In this session, we will explore the linear wave equation, which is a cornerstone of wave physics. We will begin with an introduction to the equation and its significance, before moving into a detailed derivation specifically for waves on a string. This derivation will involve applying Newton's second law and using the small angle approximation. After establishing the general form of the wave equation, we will see how it applies to various physical phenomena, including an introduction to the characteristics of sound waves. The linear wave equation is a mathematical description that completely characterizes wave motion. Any wave function, which we represent as y of x and t, serves as a solution to this equation. By studying this relationship, we can derive an expression for the speed at which a wave travels through a medium. While we often use strings as a primary example, it is important to remember that this equation is fundamental to many other forms of wave motion found in nature. To derive the wave equation, let us consider a traveling wave moving along a string that is held under a constant tension, T. We focus our attention on a very small segment of the string, with a horizontal length represented by delta, x. Because the string is vibrating, the ends of this small element, labeled A and B, make small angles with the horizontal x-axis. These angles are denoted as theta A and theta B. The net vertical force acting on this specific element is calculated by taking the vertical component of the tension at point B, which is tension times the sine of theta B, and subtracting the vertical component of the tension at point A, which is tension times the sine of theta A. We can simplify our force equation by using the small angle approximation. When the angle is very small, the sine of the angle is approximately equal to the tangent of the angle. This allows us to rewrite the net vertical force as the tension multiplied by the difference between the tangent of theta B and the tangent of theta A. In calculus, the tangent of the angle at any point on the string represents the slope of the string at that point. Therefore, we can express these tangents as partial derivatives of the vertical position y with respect to the horizontal position x. The net vertical force then becomes the tension multiplied by the difference between the partial derivative at point B and the partial derivative at point A. Now we apply Newton's second law, which states that the net force equals mass times acceleration. We model our small string element as a particle with a mass equal to the linear mass density, mu, multiplied by the length of the element, delta, x. The vertical acceleration is the second partial derivative of the vertical position y with respect to time. By setting our two expressions for the net vertical force equal to each other, we find that the linear mass density times the change in x multiplied by the second partial derivative of y with respect to time equals the tension multiplied by the difference in the slopes at points B and A. To find the final form of the equation, we rearrange the terms so that the ratio of the linear mass density to the tension is on one side, multiplied by the second partial derivative of y with respect to time. This is set equal to the difference in the first partial derivatives at points B and A, divided by the change in x. As we take the mathematical limit where the length of the element, delta x, approaches 0, the right side of the equation becomes the second partial derivative of y with respect to x. This gives us a relationship where the linear mass density divided by the tension times the second partial derivative with respect to time equals the second partial derivative with respect to x. The general form of the linear wave equation is written as the second partial derivative of y with respect to x equals 1 over the velocity squared times the second partial derivative of y with respect to time. This equation is universal for various types of traveling waves moving at a constant speed, v. Any function where the position and time are related in the form of x plus or minus velocity times time will satisfy this equation. Depending on the physical system, the variable y can represent different quantities, the vertical displacement of a string, the pressure variations in a sound wave, or the electric and magnetic field components in electromagnetic waves. Let us look at an example involving power and amplitude. The power transmitted by a sinusoidal wave is equal to 1/2 times the linear mass density times the angular frequency squared times the amplitude squared times the wave speed. In a given scenario, with a frequency of 60 Hz, an amplitude of 0.06 meters, and a tension of 80 newtons, the power is 512 watts. If we want to increase the power transfer to 1000 watts, while keeping all other parameters constant, we look at the ratio of the new power to the old power. This ratio is equal to the square of the new amplitude divided by the square of the old amplitude. Solving for the new amplitude, we take the old amplitude of 6 centimeters and multiply it by the square root of the ratio of 1000 watts to 512 watts, resulting in a required amplitude of 8.39 centimeters. Sound waves are mechanical, longitudinal waves that require a medium to travel through. Unlike waves on a string which move up and down, sound involves elements of the medium moving back and forth in the same direction as the wave, creating changes in density and pressure. We categorize sound waves based on their frequency. Audible waves are those within the range of human hearing. Infrasonic waves have frequencies below the audible range, often used by large animals like elephants. Ultrasonic waves have frequencies above the human hearing range and are commonly used in medical imaging and by certain animals like dogs. In summary, the linear wave equation is a fundamental mathematical tool that describes how waves move through space and time. For a string, we derived this by looking at the forces on a small element and applying Newton's second law. We found that the wave speed is determined by the physical properties of the string, specifically the square root of the tension divided by the linear mass density. While the physical nature of the medium might change, such as the pressure and density variations in sound waves, the underlying mathematical description remains the same. To conclude, let us consider 2 review questions. First, think about how the small angle approximation simplifies the derivation process by allowing us to relate the vertical force directly to the slope of the strings. Second, consider a practical application. If you quadruple the tension in a string while keeping the mass density the same, how would you need to adjust the amplitude to ensure the power transfer remains constant? This requires looking at how tension affects wave speed and how power relates to both speed and amplitude.